Hey guys, in this video I'll be talking about Darcy's law and permeability, and I'll be telling you how we can derive the units for permeability and also the definition of the units of permeability, which is Darcy. So first off, let's start with an experimental setup as follows. So imagine that this is some cylindrical medium which is filled with some kind of sediment or some kind of soil, some kind of sand, whatever it is. All right, so this is a shape that has a constant cross-sectional area AC. It has some length x. It has a pressure at P1 at the inlet and a pressure of P2 at the outlet, and some fluid is flowing from the inlet to the outlet with a flow rate Q. It's maintaining the flow rate at all times. And the fluid has a viscosity of mu. Let me just quickly change the thickness of that real quick. Yep. Okay, some viscosity mu. Okay, so now what is the Darcy's law? Darcy's law is stated as Q is equal to some constant. Well, before that, Darcy's law is that the flow rate of a fluid is directly proportional to the pressure gradient that is applied over that fluid, over that liquid. Okay, so Darcy's law can be stated as the following, which was found by Henry Darcy, who was investigating liquid flow through porous media. So K equals some proportionality constant K over the viscosity of the liquid mu times the cross-sectional area, and finally multiplied by the pressure gradient applied to that liquid. Okay, so our goal today is to find out what are the units of this value K are. Okay, so to do that we'll perform some dimensional analysis. So dimensional analysis is a technique that engineers, mathematicians, and scientists use to check the units of some particular variable. All right, so first let's rearrange our formula to get K on one side because this is what we're interested in. So K is equal to Q mu over AC dou P over dou X. All right, so for us to be able to find out the units of K, we're going to be using dimensional analysis on the MLT system, which is mass, length, and time. There's also an FLT system, but we won't be using that for the purposes of this video. All right, so let's begin with the units of Q. So Q is flow rate. So flow rate is something that flows with volume over time. It's a volumetric flow rate, yeah? So it's volume over time, which is L cubed over T, which you can rewrite as L cubed to the T times T to the minus 1. All right, viscosity. Now viscosity is a tricky one. Typically in the field we use centipoise, which can be written as millipascal seconds. So ignoring this, just doing the dimensional analysis, we have some units of pressure here and some units of time here. So we have some pressure times time. So now we're interested to find out what the dimensions of pressure are. So pressure is just some force over area. So force, if you can recall from F equals ma, is actually mass times acceleration, which is length over time squared, over some area, which is length squared. So this simplifies to m L T minus 2 L minus 2, which you can rewrite as L minus 1 T minus 2. Now let's go back to viscosity. So viscosity is pressure times the unit of time, which will end up being L minus 1 T minus 2 times time. So we get dimensions of L minus 1 T minus 1 for viscosity. Now area, cross-sectional area, that's easy. It's just length squared because that's area. Now dou P over dou X. So this one is a bit more. This is also very simple, relatively speaking. So dou P over dou X. So what are the units of dou P? Well, dou P is just a difference in pressure. So we already found what the dimensions of pressure were. So the dimensions of pressure are L minus 1 T minus 2. And the dimensions of length are L. So this simplifies down neatly. So I'm just going to use white for this. This will be L minus 2 T minus 2. Okay, so putting all of this together, K is, so what was our Q? Is just L3T minus 1. Okay, that's multiplied by the viscosity, which is ML minus 1 T minus 1. This is going to be divided by AC, dou P over dou X. So that's going to be L squared times ML minus 1 T minus 2 for the pressure. And again, divided, oh sorry, let's just put in the final term over here, which we already found to be ML minus 2 T minus 2. So what does this simplify to? So let's make some simplifications. So this L2, we know that L minus 2 and L2 will cancel each other out. T minus 1 and T minus 1 cancel each other out over here. And so we're left with L3 times L minus 1 over, so these M's cancel out as well. And we have sorry, these T minus 1 cancel out this T minus 2. So there's no more valid dimension of time over here. So we're just left with L2. So we already found that the dimensions of permeability must be L squared. So this must be in terms of area. Alright, so now let's find out what the units are. So the units of permeability are in Darcy's, okay? And the Darcy is defined as the following. So a medium with permeability of 1 Darcy allows a flow of 1 cubic centimeter per second to flow through a constant cross-sectional area of 1 centimeter squared throughout a pressure over a pressure gradient of 1 atmospheres per centimeter. Let's see, am I missing anything? Oh, viscosity of 1 centipoise, fluid viscosity. All right, so we can rewrite this as the following: K, or sorry, 1 Darcy's flow is equivalent to, let's go back to the formula here, Q. So we have 1 centimeter cubed per second times Q mu over AC dP over dx. Okay, so Q mu, now we need to type, we write here our mu, then our constant cross-sectional area, which is 1 centimeter squared, multiplied by our pressure gradient, which, if I recall the numbers correctly, the colors correctly, will be 1 atmospheres per centimeter. Alright, so now let's do some simplifications. We see that this cm squared and this cm will cancel out to just leave cm. Centipoise, so this is one fact that we can make use of. 1 centipoise again is 1 millipascal second. So that's 1 times 10 to the minus 3 Pascal seconds. Alright, so let's rewrite what we already know. So now this centimeter cubed will cancel out with the cm at the bottom. So what we are going to be left with is 1 cm per second times 1 times 10 to the negative 3 Pascal seconds. So we know that 1 atmospheres is the same as 101,325 pascals. So we can just rewrite this as 101,325 pascals. So these seconds cancel out, these pascals cancel out. So we are left with, finally, 1 Darcy is equal to 1 times 10 to the minus 3 centimeters squared over 101,325. And that's it. That's the definition of 1 Darcy. So 1 Darcy is ultimately equal to, so let me just get my calculator and pop this real quick. And for students taking petroleum engineering or hydrology, geotechnical engineering, whatever it is, you probably want to memorize this value. 1 Darcy is 9.869 times 10 to the minus 9 centimeters squared. So field units are typically expressed as millidarcies. So 1 millidarcy is just, you just need to divide this by 1,000. So you'll get 9.869 times 10 to the negative 12 centimeters squared. So now the exercise for all of you watchers out there, in the comments, I want you to tell me how I can convert 1 millidarcies in terms of meters squared and how I can do that in terms of feet squared. Okay, so that's it from me today. Thank you for watching. Leave a comment, like, and subscribe. Thank you very much.